Hi, we are in 3.3, which uses sections 3.1, that makes sense, and 3.2. In 3.1, we did conditional probability, and you can kind of see below in this first example, you can see the conditioning here. So I need what we did in 3.1, but I also need what we did in 3.2, which was the multiplication rule. And again, I think what we do, 3.3, the law of total probability, you naturally do this. You just don't think that you're doing, I mean, I don't think you sit down and say, oh, I'm conditioning on X, Y, and Z, but that's what you're really doing. You're trying to find the probability something happens, like here, you're pulling a green marble or something out of a box, giving all possibilities of things that came before it. So, anyways, that's how I'm going to use 3.1 and 3.2. I think it takes, I think I wrote this first so I could just give you an example to show you it's not bad, and then we'll do the definition. So imagine you have a box. So box one here, we'll just say box one. It has marbles in it, has 4 green marbles, and it has 5 brown marbles. And then box number 2, you can probably hear the dogs walking around. Their toes are clicking. 6 green marbles and 8 brown marbles. Okay, so I'm going to draw a marble out of box 1 and put it into box 2. And then I'm going to draw a marble from box 2. And I want to know what's the probability that the second marble chosen, the one that's drawn out of box 2, is green. So I want to find probability box 2, I pull a green marble. So I guess I don't need to write this all because I put up the solution. So probability green comes from box 2 is you get a green from box 2, well, I'm not going to say given yet, green from box 2 and green came from box 1, or, and notice I can multiply these because add them because they're mutually exclusive, green from box 2 and brown from box 1. So by definition, we did the multiplication rule. To find the probability of this happening, you're just conditioning on the first event. So the probability of pulling a green out of box 2, given you got a green out of box 1, times the first place you even got a green out of box 1, plus the probability you pull a green out of box 2, given you pulled a brown from box 1, times the probability that even happened. So I hope my numbers here make sense to you what I'm doing. So I mean, what's the probability I pull a green out of here given a green came over? Because if a green comes over, right, it changes the number of greens I have over here to 7. So that's where you're seeing the 7 over 15. I don't feel like I said that perfect, so if you want me to do another one on that, but I hope that kind of, I hope that gives you the idea. Maybe I should go through another one better. The law of total probability just says if you have a sample space S that's partitioned by a bunch of events A. So imagine this is event A1, this is event A2, A3, A4, A5, A6. These are all mutually exclusive. They're not intersecting. So if you have some other events, let's call it B, and B is, as you can kind of see, B is going over the A's. I mean, it actually doesn't have to intersect all the B's. I mean, all the A's at all. This is my event B here. And notice there's a probability B occurring if it's sitting in A2, and B occurring if it's sitting in A1, and B occurring if it's sitting in A4. I mean, and there's some, you can see here A5 is much larger. So, then for example, a little A2 over here. So all I'm doing is saying, what's the probability B is going to happen given it's sitting in A2? What's the probability B would happen it's sitting in A1, A3? So what the law of total probability is saying is, what's the probability B happens when B is defined over a sample space that's partitioned by these A's. So to be able to use this theorem, what you need is a sample space S that the union of all these mutually exclusive A's make up S. So again, just imagine this picture, and all this says right here is that every AI and AJ, all these events are empty. There's no intersections of any of these. So then if you take some event B that goes across your sample space here, the probability of B is the probability B given it's in A1 times it's even in A1. the probability B happens given it's an A2 times the probability A2. And again, like the probability you're an A2, let's hear over here is small. The probability you're an A1 is bigger. So you're really just taking a weighted average of B happening conditioning on A. So here, if you want a very compact formula, you're just finding the probability B happens over the mutually exclusive events A1, A2 up to AN. So that's the law of total probability, and I think I made it look more difficult than it actually is. Let's pull up a. Oh, here's like example 4 is probably I think pretty nice. Farmer Green went to the market and got a handful of seeds. Approximately 2/3 of them were fresh and 1/3 is old. So imagine you have these seeds here, right? So 2/3 of your sample space is fresh, and then 1/3 of your sample space is old. And now germinate happens. So if let's go to another color actually, or if I can make another color. It's like red. Red will be the event of germinating. So there's a germinating given you're in the fresh, and then there's a germinating given that you're in the old. So the probability I grab a seed and it germinates is the probability it germinates given it's sitting in here, the old category, or the probability it germinates given it's sitting here in the new or fresh category, times the probability it's even sitting over here, times the probability. So that's where I'm just using that rule. And yeah, this is another one I kind of like. What's the probability, you pick somebody and they think the president's doing a good job? I think that's pretty dependent on the party, whoever you ask. So the probability someone thinks the president is doing a good job depends on Democrat or Republican or other. And now I'm just using the multiplication rule to say good job given Democrat. And what's the probability, what proportion of people in the world are Democrat? So good job given Republican times Republican. You kind of get where I'm going here with this. I'm just, again, conditioning. And notice that Democrat, I'm assuming Democrat, Republican, and other are mutually exclusive events. So, imagine you don't have any overlap here. And that's pretty true, right, in our political system. And what we're going to do then in 3-4 is called Bayes' theorem, and we're going to be trying to find then the opposite conditional. So I think this is a very interesting question where we're going for in 3-4 is now we can find the probability somebody thinks the president's doing a good job. But now given someone says, hey, I think the president's doing a good job, I want to find the probability that they're, let's say, Democrat. So notice I'm trying to find, this was the conditional probability I had up here, and I'm trying to find the opposite one. That's what Bayes' theorem is. And I think it's interesting. That given good job, the probability Democrat's going to be much higher than the probability given they thought it's a good job that it's a Republican. Given a good job, it's most likely a Democrat. And, well, sorry, too, I shouldn't probably be talking so much politics, especially. I know we have a lot of international students, so sorry about that, but I'll just say that Obama is a Democrat, so people here would, if they think he's doing a good job, they're coming from the same party. Okay, don't worry about that, but I hope you can kind of see what the law of total probability is doing. So probably not the best video we ever had. Next week I'm going to try to make a couple on a whiteboard. So I'll talk again soon.